Hi guys, welcome back. This is section 10.1, part 3. We're going to start off with the idea of converging versus diverging sequences. So if we're going to talk about limits a lot right after sequences, but we talked a little bit about limits at the beginning of the school year, and the idea behind a limit is for a function that is getting closer and closer to a number. So if for a sequence to converge, then the sequence as the terms are going forward from first term, second term, third term, fourth term, if it's converging, they're getting closer and closer to a number. They could be coming at it from two different directions. They could be coming at it from the same direction. So here's an example. If you see an alternating sequence, say, it's doing this, but it's getting really, really close to some number, then we would say this guy is converging. And it's really easy to see them converging when it's an alternating sequence. But another sequence that converges would be, for example, something that maybe is taking on a logarithmic or an exponential. This guy is getting converging down to whatever this point is up here, right? So it's getting closer and closer to some number. The distances between them is getting smaller and smaller. The vertical distances, I should say. It's getting smaller and smaller. Opposite of that would be diverging sequences. Let's see if I get all those. All right, a diverging sequence for the alternating, again, alternating are much more visually appealing to tell whether they're diverging or not. But this is very obvious that these points are getting further and further apart from each other. One that's less obvious is just like a linear sequence like so. That guy is diverging. It's harder to tell because the distance between them is always the same. But are these guys getting closer and closer to some y value? No, they're going to continue on and on forever. And so we say that they diverge instead of converge on their number. So let's look at some examples. Here's this a sub n is equal to negative 4,000 times negative 1/4 to the n. So you guys are new to sequences. Anytime you see a negative sign raised to an n power, this is going to be something called an alternating sequence. Why? Well, this would be negative 1 to the first power for the first term, so it's going to be a negative times a negative. So a sub 1, we don't know really what it is yet, it's going to be positive. But then when we've got a sub 2, this guy becomes a squared. So this guy is negative times negative, which is positive now times a negative, so the next one's going to be negative. If I go back to a sub 3, negative raised to an odd power is negative, times the negative is positive. So notice here how my signs are alternating back and forth. So it's called an alternating sequence, and this is what their values look like. I think these numbers are a little off. I'm pretty sure this guy here should be below the line and then above the line and below, but you kind of get the idea that we start way up high, we go down, it's coming back up. I think it does something more like this, and this, and this, and this. And we're getting closer and closer to what value? 0. So we would say this is a convergent sequence, and it converges to 0. Second example is this one here. Is this one alternating? Yes, it is. Remember, you've got this negative inside the parentheses being raised to an n power. So when I've got an odd power, this is negative to the first power would be negative. If I've got an even power, it's going to be positive because negative squared is positive. So it's another alternating sequence. And let's see what this one looks like when we plug in some values. So notice for this one, we start off small here, and then we go to a positive and then negative and positive and negative, but now we're pulling away from that 0 line. And so this would be an example of a divergent sequence. All right, and so that was it for day 1. I'm going to go ahead and plow into day 2, which we're talking about today in class. So we've got series. A series is just the sum of all the terms in a sequence. So we talked about yesterday, we've got finite sequences, like this guy here where we've only got 5 terms. So therefore, it's going to have a finite series. I can add those 5 terms together. Boom, done. And then we also had infinite sequences yesterday, which we said go on and on forever, and that was our dot, dot, dot. And so that means their sum goes on and on and on forever. So sometimes we think, hey, well, we can't figure out what that is, but we actually can. And we're going to first start off with this concept of finding the nth partial sum. So if I ask you, and it's denoted as S sub n, that's the nth partial sum of an infinite series. And so if I asked you to say, find the fourth partial sum of this guy here, you're going to be looking for S4, the sum of the first four terms. So that means you just want to know what is the sum of 1 plus 3 plus 5 plus 7. And that would be the fourth partial sum for this infinite series. So let's look at some examples. Find the fifth partial sum of a sub n is equal to n squared minus 3. So in order to find the fifth partial sum, I've got to find the first 5 terms of this sequence. So I've got 1 squared minus 3. I've got 2 squared minus 3. I've got 3 squared minus 3. Let's see, 9 minus 3 is 6. 4 squared minus 3, 16 minus 3 is 13. 5 squared minus 3, 25 minus 3 is 22. So the fifth partial sum then is just adding those 5 numbers together. So S sub 5, the fifth partial sum, is going to be negative 2 plus 1 plus 6 plus 13 plus 22, and that is equal to 40. All right. This one says find S sub 4 of this sequence. That means the fourth partial sum. Again, in order to find the fourth partial sum, you need to find the first 4 terms. So this would be 6 over 2, which is 3. 6 over 2 squared, 6 over 4, which is 3 halves. 6 over 2 cubed, 6 over 8. Let's see, that would be 3 fourths. And then 6 over 2 to the 4th, 6 over 16, which is 3 eighths. So the fourth partial sum is going to be 3 plus 3 halves plus 3 fourths plus 3 eighths. What do we need to have in order to add these guys all together? Hopefully you said a common denominator. In this case, they all go into 8, but 8 can't go into any of them, so 8 is my lowest common denominator. What do I have to multiply this numerator by to get to the common denominator? I have to multiply that by 3, so that's going to be 24. This had a 2. 2 times 4 gives me 8, so 3 times 4 gives me 12. 4 times 2 gives me 8, so 3 times 2 gives me 6. And this is already 8, so I don't change the numerator. If we add all of those guys together, we get 45 eighths. So the fourth partial sum of this sequence is 45 eighths. Let's do one more, and we'll stop the video. Fifth partial sum of this guy. In order to find it, we need to find the first 5 terms. All right, this is going to be negative 3 to the first power minus 2. That's negative 3 minus 2, which is negative 5. Negative 3 squared minus 2. That's going to be 9 minus 2, which is 7. Negative 3 cubed minus 2. Well, that's negative 27 minus 2, which is negative 29. Negative 3 to the 4th minus 2. Negative 3 to the 4th would be 81 minus 2 is 79. And then negative 3 to the 5th minus 2. Negative 3 to the 5th is negative 243 minus 2 would be negative 245. So S sub 5 will be negative 5 plus 7 minus 29 plus 79 minus 245. And that would be negative 193. And that's my fifth partial sum of this sequence. And that's it for this video. Come back and we'll talk a little bit about sigma notation, and then we'll be done with section 10.1.